All right, let's get started. So today we're talking about force and oh yes, wonderful, got the green one. Today we're talking about force and motion. Okay, there's supposed to be a whole bunch of math involved in this, but I'm not going to make it very math heavy for you, right? So we discussed this a little bit last week already, where if you have gravity, right, an acceleration due to gravity is 9.8 meters per second squared, right? And it's a constant acceleration at 9.8 meters per second squared. So what that means is, excuse me, every time a second passes, the number gets squared, right? Excuse me. I just had some beef jerky for like a snack, and now I'm all itchy in my throat. Anyway, so every second that passes, the number gets squared, and that's why it's 9.8 meters per second squared. Okay. So the thing I want you to notice about that is that as time increases, right, the velocity also increases, but the velocity increases in a very linear fashion. Okay, it's important to know. Excuse me, it increases in a linear fashion. Okay. Oh, then you brought a whole gallon. God, so responsible. A gallon. Sorry, whole dozen. Whole dozen. Sorry, I'm hard of English because I'm Asian. So anyway, so now that you know, this is very important. The increase in velocity is linear in an acceleration, right? Your very first question is this: acceleration due to gravity is what? Yeah, sounds good. I literally just told you that this is very important when I circled it there. Yeah, I can pick it up in just 1 second. Oh yes, go ahead, Derek. What a nice guy he is. I don't care what anyone says about you. I don't care what anyone says about you. I swear, if any of you get this wrong, I literally just said this on the previous slide. I swear, if any of you get this wrong, this is your first free giveaway point for doing so well on the exam. Everybody in? Okay, that's 20 people. Are there 20 people in the room? Um, 21 people. Okay. Oh, Carly, you're always the problem child. 6, 10, 11, 17. Oh, did you count for me? Thank you so much. How did you know I was counting? Oh man, that's funny. Oh, unbelievable. I literally just said okay. Huh? Someone must have hit it. Someone must have hit it wrong. Okay, so everybody got it right except for one person, right? To that one person, I hope you just hit the wrong button. The answer to this is literally linear because I literally said it just a second ago. The increase in velocity is linear, right? Linear. Okay. All right. So that was just a quick review of what we did last week, right before the exam. So the thing about it is that gravity is, or things that are falling do have issues sometimes when there's things like wind resistance that can slow things down. And so these are what we call frictional effects, right? Frictional effects are air resistance or wind resistance. Usually, when we're doing a problem for free falling object, we neglect wind resistance, right, or air resistance. But it's there. It's definitely there. So what you can see here is actually a tube, right? And there's a feather in there, and there's a coin in there. And what this little thing here, which it doesn't really tell you what that is, but it's just a vacuum, and it's sucking all the air out. And so inside of a vacuum tube, there's no air resistance at all, right? and two things that are completely different weights, the feather and the coin, will fall at the same rate and hit the ground at the same time. Okay, excuse me. And so, good old astronaut David Scott did the same thing, except he did this on the moon, where he had a feather and a hammer, and the moon doesn't have any atmosphere, and so since there's no atmosphere, there's no wind, right? And or air resistance. That's why you have to wear a spacesuit, right? And he dropped a feather and a hammer, and they both fell at the same rate, and they both hit the ground at the same rate, right? Because there's no air on the moon. If you didn't know, that was the moon right there. Okay. So going back a few millennia, right? Galileo is actually the one that that did the very first experiment that proved or demonstrated that two free falling objects will go at the same rate regardless of weight, right, and hit the ground at the same time due to the acceleration of gravity at 9.8 meters per second squared, right? And so he was at the top. Good old Galileo was at the top of the Leaning Tower of Pisa, which is a little scary because it looks like he's about to fall. Is he a little big? Is he too big to be in that building? I don't know. Not to scale, I guess. Anyway, you drop it. He's dropping a small rock and a big rock, and they're both falling, and they're falling at the same rate. Okay, they're literally both falling at the same rate. They're both falling at the same rate. So things to get out of these last couple of slides, right? Just to know, right? If we neglect wind resistance or air resistance or frictional effects, right? Then the acceleration is constant. The velocity change is constant acceleration, and free falling objects will fall at the same rate, the same velocity, the same acceleration, and they will hit the ground at the same time if you let them go at the same time. Okay? Got it? I see people writing, so that's why I'm just kind of blabbering until people stop writing. I posted these notes earlier today. I apologize for not getting them over the weekend, but they're not that complicated. So your next question is this: what would hit the ground first if you dropped it on the moon? The Hulk, Ant-Man, Captain America, or none of these? Do you need me to scan it for you, Carly?
It just must be this angle over
It must be. I'm trying not to get in people's way. Well, Henneka's over here and she can get it.
Mine doesn't work from this angle.
That's fine. I'm just
It
playing.
doesn't work from my angle either.
It isn't?
I've tried too.
Oh, when you did her
Mine
phone?
and hers, yeah.
Maybe it's the case you have.
The case is like covered with.
Oh, well, sometimes they can clip off the side and like trying to get it from the edge, but you're right. It shouldn't. Maybe it's because your phone is so new.
Maybe it doesn't like you.
Oh, Derek's not having a problem. Is it not scanning? You want to just try to scan it from down there on my iPad? It's on the iPad too. I'll turn it this way for you so it's easier. Did it work? Oh, that's a great idea. I should just bring the iPad over for you guys to scan it when we get to another question. Great idea. Why didn't I think of that before? All right, let's see what the answers were. I believe I called this question the Hulk. The Hulk. I did. 22 responses. Let's see what the responses are. Yay! Woohoo! Everybody got it right. Yes. In fact, the answer is none of these. Why? Because on the moon there's no wind resistance, right? The Ant-Man will fall at the same rate as the Hulk, will fall at the same rate as Captain America, and all three will hit the ground at the same time. Okay? Good stuff. Good stuff. Okay. So, this is the extent of the math we'll be doing, right? What about the distance it travels, the object travels, right? So here we have an equation. And in this equation, we have distance, and it equals 1/2 times g times t squared, right? So literally d is distance, g is gravity. That's that 9.8 meters per second squared, right? And then t is time. Okay, t is time. Um, so basically, we can use this equation to figure out the distance after a certain amount of time, right? So it's a pretty easy equation to do. So looking at this picture again that we had before, right? Looking at this picture that we had before, and this equation, you can use this equation right here to figure out the distance that the ball traveled as it fell down, as it falls down, right? So if you're to plug in 9.8 meters per second squared there, right? And then you plug in time is at 1 second, your distance, and you multiply all that out, your distance becomes 4.9 meters, right? If you were to change it up and say um, 2 seconds, right? Would you use this number here? No, you'd use the 9.8 meters per second squared because that's gravity's acceleration. So 9.8 meters per second squared times the time, which is 2 seconds squared, you'll get 19.6 meters distance, right? And then again, if you were to put gravity there again, 9.8 meters per second squared, along with the time at 3 seconds, right? You get a distance of 41.1, right? So super simple math here, okay? Don't think too hard about it. The worst I'll do to you is give you a time, right, to plug in. And then you just have to remember that gravity is 9.8 meters per second squared, okay? It's always going to be that, okay? So notice here then that the velocity is proportional to time. So remember that the v final equals the v final, the velocity when we're done, right? Right here, the velocity when we're done is equal to the acceleration times the time, right? So quite literally then, if you were to say for 1 second right there, if you were to have 1 second right there, plug that into t, and then a would be acceleration. So a and g are the same thing for gravity. So the acceleration again is 9.8 meters per second squared, right? Then your v final is going to be that number right there, right? So that's how you figure out how fast it was going. That's how you figure out how fast it was going. So really, right, all you have to do if you had a ball or you had anything, you wanted to figure out how fast something was going when it fell, you just have to time it, right? And you can figure out how fast it was going because you already know what the acceleration of gravity is. Does that make sense? Right? Um, it's pretty simple. It's pretty simple. Both of these equations are super simple. Like again, the worst thing I can do to you is plug in, a final I might say plug in you're going at a speed of 10 meters per second. How much time passed by, or something like that. It won't be that bad. Okay. There's easy plug and play. No, wait, that's all right. Plug and chug. Easy plug and chug stuff. No more conversions. No more fence posts. Just easy plug and chug. Okay. So the thing I want you to notice about this then is that when you have, remember from the previous slide, right? Uh, the the velocity over time had a constant, not a constant, a linear progression. It got larger linearly, right? As time passed, and distance, it's not distance, velocity. Velocity is on the y-axis, seconds here, and so velocity just had a very nice increase in linear increase. But when you compare that to distance, the distance is actually exponential, right? In the same time that the velocity is going like 6 seconds, and it was at a very nice, linear relationship, the distance actually exponentially increased in that time. Okay, so that's the thing you need to know, right? When we're talking about a increase in velocity, excuse me, the velocity is proportional to time, right? Like I was saying before, but then the distance is proportional to time squared. And that's why the equation here is t squared, right? And that's why the gravity's where'd it go? There it is. Gravity's constant is second squared, right? Gravity's constant is second squared. So that's a very important thing to know. Velocity is proportional to time, and then distance is proportional to time squared. And you know that because gravity's constant is 9.8 meters per second squared. Okay. All right. So here's your next question. Distance is proportional to what? You can expect that, questions on the test will be like this, where I'm going to ask you, this is this kind of relationship, this is that kind of relationship, proportional to what? Go ahead. Do you need the iPad? Okay. All right, let's see how everybody answered this one. Now it's just a test to see if you guys are paying attention. It's a good time. Excuse me. 17 responses so far. 20 responses so far. 21 responses. One more. Oh, that's why. Okay, so most of you got it right. The one person who got it wrong, remember, distance is proportional to time squared, right? That was the previous slide. Distance is proportional to time squared. Okay? So make sure you memorize that. So the other kind of scenario we can have is we can throw up a ball straight up into the air. Okay? We can throw up a ball straight up into the air, and it can come back down again. So as you're doing this, you can see that the velocity is going up, right? But then gravity is pulling it down at the same time. Okay? When you reach to a point where like the velocity is zero, why is the velocity zero up there? It changed direction, right? It went all the way to the top of the peak of where it was being thrown, and then changed direction, and it's coming back down again. So that's a question I might ask you, right? When you're throwing a ball, other than when it lands and when you're holding it, where's the velocity zero? Well, it's at the point where it changes directions, right? At the peak, at the very top. So once it changes directions, right, gravity is still pulling on it to go down right here, but since there's no velocity upwards, it's just going to come down. And now you have both gravity and velocity going in the same direction. Okay. And again, the velocity equals zero once the ball lands, right? Or ends up where it started, basically. Okay. So just to know, right? Acceleration is due to gravity occurs in both directions. Going up is minus, right? Going down is plus direction. Okay. And then the interesting thing to note here, right, of course, is that when the ball returns to the starting point with the same speed it initially had, the initial velocity is equal to the final velocity, right? Which makes sense because it was not moving when you before you threw it, and then when it landed, it's also not moving, right? Does that make sense? Okay, good stuff. Good stuff. All right. So one more time, initial velocity equals the final velocity. Then the velocity is also zero at the peak because the ball changed directions at the peak. Okay. So your next question is this. When you throw a ball straight up in the air, which of these is true? Which of these is true? Right. They were supposed to fix this for me already. Getting tired of having to turn the screen around. 16 so far. $20 people. Oh, here. Or is it asking you to sign in every time, or are you just going straight to the question? Who said that? You have to sign in every time?
Yeah, but I wanted like a private VPN
Oh,
browser weird stuff. So.
that's why. There we go. Okay, once again, a single person got it wrong. I'm starting to think that the single person that got it wrong is just getting it wrong for the heck of it, right? Just to annoy me, maybe. But just like I said in the previous slide, right? The velocity, the initial velocity equals the final velocity, right? And so the answer here would be A. Would be A, right? Initial velocity equals final velocity. So the things you can do with that, like, because, there's, we were talking about our velocity equations before. You had initial velocity and final velocity, right? So all that stuff would like zero out, right? Because it started at zero when you threw it, and then when it lands, it's zero again, right? So you don't even have to worry about it anymore. Okay. So that's one type of motion, right? The next type of motion we're going to talk about is uniform circular motion, also known as centripetal force, not centrifugal force, but centripetal force, right? And so, um, although an object in uniform circular motion has a constant speed, it is constantly changing directions, and therefore its velocity is constantly changing directions as well. Okay, and I'll show you a picture of that in a second. Since there's a change of direction, is there a change in acceleration? Sorry. Since there is a change in direction, there is a change in acceleration. So the question would be, what is the direction of this acceleration right here, right? And the answer to that question is that the acceleration would be in right angles to the velocity towards the center of the circle. And I'll show you that in a second. I'll show you a picture of that in a second. I know people are writing. You don't have to copy my notes. I post them for you. Gotcha. Then you can always listen to my lectures and then and copy the notes down with the PowerPoint that I post for you. Okay, so let's take a look at what this looks like. Okay, so here we have a race car. Okay, and it's going around a track in a circular motion. Right. This is just a circular track, not a crazy maybe a figure eight track or something like that. It's just a circular track, right? Excuse me. You have friction supplied by the tires of the car, of course, and then the car remains on a circular path as long as there's enough centripetal acceleration, right? So when I was talking about before in this previous slide about right angles to the velocity and generally toward the center of the circle, right? This is what's happening here, okay? When a car drives in a circle like this, a race car drives in a circle, it's using centripetal acceleration. So its velocity is trying to make it go straight out like that, right? Like fly out that way, or fly that way, or fly that way. Not in a circle, but just go straight, right? But when you turn your wheel, right, so that you're going in a circle in the centripetal acceleration path, there's another vector here, right, that pulls you towards the center of the circle, and that's what keeps you from flying off and veering off into the crowd over here, right, or over there, right? There might be a a person over here. There might be a person right there. And it's waving a flag, right? And you definitely don't want the car just veering off and hitting that person, poor guy, right? Luckily, if you have control of your vehicle and you're still turning that wheel, no, that person's probably safe. Either that or they just keel over and die, right? Because you crashed into them. Anyway, right? So that's something you need to know as far as concepts go, which is this right here, right? The direction of the velocity is right angles. Sorry, the direction of the acceleration is right angles to the velocity, and then generally towards the center of the circle. That's important to know. So the velocity is going straight. It's going to crash into that guy right there, but the centripetal acceleration pulls you towards the center of the circle. Okay. So again, we have another very simple equation, super simple equation here. We have centripetal acceleration equals the velocity squared divided by the radius of the circle. Okay, divided by the radius of the circle. There's not going to be any more of those long problems where you have to figure out, meters per second to miles per minute or some crap like that anymore. Now they're all just quite literally just plugging in numbers and just doing simple math, okay? One-step problems, okay? So I'll either give you a velocity where you can just square it, right? You'll know the right radius and then you can find the acceleration, or you know the acceleration and the radius and you can find what the velocity is, right? I would never do that actually. I'll never ask you what the velocity is, but I'll definitely might ask you what the acceleration is. And then also, if you have both of those, the acceleration and the velocity, you can figure out how big the track was, like how big the circle was, the track was. Okay, it's a good time, I think. Okay, so let's do a quick example here. Just a quick example. If AC equals V squared over, I forgot what it was. What's the formula? R. Thank you. Right? Quite literally, all you have to do, right, is plug in here, determine the magnitude of the centripetal acceleration of a car that's going 12 meters per second on a circular track at a radius of 50 mils, 50 meters, right? So quite literally, just AC equals 12 meters per second divided by, what was it, 50 meters. Okay. Oh, not 5 meters, 50 meters. Sorry, 50 meters. Okay. 50 meters. And it's that easy. Someone just do that math and you're done. It is that easy. Say again? The 12? Oh, I'm sorry about that. Ha ha. Yeah, sorry about that. That's a typo right there. Yeah, that's a typo. It's totally a typo. Totally a typo. Thank you for catching my units. Okay. What is that going to be like?
So you don't square 12? Then you square the 12, not the unit.
Oh, right. There you go. What's 12 on 12? 144, correct?
Yeah.
Yeah. And divided by 50? Yep. But yeah, it's pretty simple. Pretty simple. 2.98? 2.88? Yeah, so yeah, it'd be 2.9 because for two significant figures. Cool. Okay, so here's your next question. What is the direction of what is the direction of centripetal acceleration? I was hoping we'd get done with lecture pretty early today so that we could go over in the lab and work on some of your experiments, but there's somebody else in the lab right now that might not get finished in time. So we'll see how that goes. Who needs to scan? Carly, you need it? So what number are we on now? New form. Not new form. I don't want a new form. Cancel. How do you cancel that? Forms. And centripetal. Still missing a person. There we go. Okay, so now this time, again, most people got it right. The answer is it's always going towards the center, right? Right angle to the velocity, right? It's definitely not the, so there's like three people that said going away from the center, right? Remember, if you go away from the center, you go and you hit that guy that died over here, right? That guy that's going away from the center and the guy died. You don't want that guy to die. So think about that during the test. You don't want the guy to die, so you're going to go towards the center. Okay? Right? Okay. All right. So the last type of motion we're going to be talking about today, the last type of motion we'll be talking about today is projectile motion. Okay? It's projectile motion. And basically what happens here is that you can throw an object or you can shoot an object, right, like a bullet from a gun, and it will eventually, like it goes horizontally, but gravity is always pulling it down as it's going, right? And eventually it'll hit the ground. Okay? Eventually hit the ground. So an object thrown horizontally combines both a straight line with and vertical motion, right? Each of which act independently. You see here, this ball here is throwing, it's going horizontally, but then gravity is pulling it in a vertical motion to go down to the ground. Okay. So again, we can neglect air resistance. We pretend that there's no wind resistance or air resistance, right? A horizontally projected object travels in a horizontal direction with a constant velocity while falling vertically due to gravity. Okay. And you find we do that a lot. We just neglect air resistance. Okay. So let's look at a couple of different examples of throwing something in, like in instead of throwing a couple examples ago, we were throwing a ball up in the air, straight up in the air, and it was coming straight down again, right? So now we're going to put a little direction on it, and it's going to go forward instead of falling down, instead of going up, straight up, and straight back down again. So the reason why so this is just explaining why it's both a horizontal component and a vertical component, right? You are throwing it in an upward direction at a certain angle, right? So that's the vertical component here. And remember, of course, at the very top, when it changes direction, the velocity is 0. When it starts, the velocity is 0. When it ends, the velocity is also 0, right? But the new thing we're adding to it is this horizontal component where you're pushing it forward like that, right? So combining these two things together is why you get this nice little elliptical shape here, right? This nice little elliptical shape. Okay. The same is still true though, right? When it's yeah. I don't want to say that part yet. You can definitely figure out like what these angles are and what the speed is and all that stuff, but we won't get too deep into that. So let's talk about throwing a football. It's a very similar thing, right? Very similar thing. In throwing a football, the horizontal velocity remains constant, but the vertical velocity changes, like that of the object thrown upward, right? So again, right here, when you first throw the ball, right, the football, the velocity is going towards the like going to the right, going forward, and going up, right? And it keeps on doing that. It keeps on doing that until you get to what point? The point where the ball changes direction again, right? The ball also changed direction again. So when the ball changes direction, the velocity is zero. The y velocity, the up and down velocity is zero. So that's a good thing to remember right there. When you're doing one of these projectile questions, the up and down, or also known as the y velocity, becomes zero because it's no longer going upward, right? But the forward velocity is still the same, right? The forward velocity is still not the same, but still going forward. Right? When the when the ball changes objects, it starts to fall because of gravity, right? Gravity takes over right here. So now you have the velocity going downwards, but you still have forward velocity going forward. And when you have forward velocity going downwards, you have a negative velocity, right? We talked about that in a previous slide. And it just keeps on going until someone catches it, right? Or it's an incomplete pass. Okay? And it falls onto the ground. So this is super similar to throwing a ball straight up in the air and having it come right back down again. But the difference now is that you have a forward motion as well, right? And until the pass gets completed or the ball falls to the ground, right? You're always going to have that forward motion in the positive, right? Not in the backwards and the negative. But the thing to notice, though, is that the upward velocity switches to downward or negative velocity after the ball changes direction where the velocity is zero. Okay? Good stuff. Good stuff. Good stuff. Any questions so far? This is all super conceptual stuff, right? Not a lot of math going on here. So let's talk about golf now, then, right? Oh, that's too bad that Kate's not here. She's a golfer. She's at like a golf tournament right now. It's too bad. Anyway, if air resistance is neglected, projectiles have symmetrical paths, and the maximum range that is attained is at a 45-degree angle. Okay, so what's happening here? Remember, we're just doing this without air resistance again, right? We're doing this without air resistance again. Say this person here drives the ball and he swings, and he didn't follow through very well, right? And the ball is projected from the tee at only a 30-degree angle, right? The thing I want you to notice here is that you go up and down right in the middle, right, of this angle right here, of this path, and you can see that the path is symmetrical, okay? Right? Right when the ball changes direction to go back down again because of gravity, you can see that both sides are symmetrical to each other, right? So the lower the angle that the ball is projected or shot from, right? The shorter the distance the ball goes. Okay, and you would actually think that, say, if you shot it at a higher angle, like a much wider angle, say 60 degrees instead of 30. Okay, we can draw the line down again like that, where we denote that the v equals 0 up here, right? And when that happens, right, it comes back down again, and it actually goes the same distance as the uh, 30 degree ball. right? Because both sides are symmetrical. That side is symmetrical, and that side is also symmetrical, right? And then if you notice that 45 is right in between 60 and 30, right? And so that's why it goes the same distance regardless of whether you're doing the 30 or the 60 degree, right? The same thing would happen if you were to say do a uh, a 55-degree angle, right, and a 40-degree angle, right? So what that means then is that the furthest that a ball can travel, right, would be accomplished by shooting the ball, right, driving the ball, to use golf vernacular, by driving the ball at a 45-degree angle, right, at a 45-degree angle. And again, you draw a line right down the middle, and you see that both this side and this side is symmetrical to each other. And so that's why we can predict very closely how far a ball travels when it's hit, or even how far a bullet travels when it's shot, right? If we bring in air resistance, right, which is really what golf is about because it's always windy when you're golfing for some reason, right? We saw this line here, the red line, with no air friction at all, right? With no air friction at all at 45, right? But then with air friction, even at a 45-degree angle, which is the max the ball can ever travel, right? The max that the ball can ever travel, you're getting like, I mean, you're trying to shoot for this 45, but then you get like 38 degrees, right? And the 38 degrees goes a little further than the 45 degrees here during the air friction. So with air friction, you actually get a little bit more distance. Get a little more distance if you have a more narrow angle, right? As compared to this one here, which makes kind of sense because like the lower you shoot it, right, the more flat you shoot the ball, you drive the ball, it can go under the wind, the air, right? There won't be as much air resistance. So, but if you go too high with it, it'll keep the ball up there in the air for a little longer. It won't let it go as far. Okay. So there are some things that you should take note of when we're talking about projectiles and athletic considerations, right? Oh man, see, I wish the golfer were here. She would have enjoyed this. Um, the angle of release, and the angle of release, right, is of course this right here, the angle of release right here. Okay. And then the spin on the ball, right? A spin on it will actually make it travel a little further, right? It kind of defeats the wind resistance, kind of like when you put a spin on a football. The size and shape of the ball, right? Uh, a golf ball will go probably a lot further when you hit it with a golf club than a football will, right? And so the speed of the wind, the direction of the wind, right? Um, and then weather conditions, of course. If it's humid, if it's a humid day or it's rainy, you're definitely going to have a lot of resistance there. The field altitude, where how much air is present. So the higher you get in above sea level, the less air pressure there is, right? And there's less atmosphere, and so then there's less air resistance when you get higher in the atmosphere, right? And then lastly, the thing to note here is the initial velocity, like how fast is the ball going when you first hit the ball. In order to make it out of the park before gravity brings it down, a baseball must leave the bat at a very high velocity, right? A very high velocity. So the next slide is a whole bunch of equations that you don't really need because you've already learned them all, right? You literally have already learned them all because you've learned these already on the last test, right? And you learned these today, right here. You learned that on the last test, okay? The only thing I really want you to remember is the 9.8 meters per second squared, right? Or if you're an American, if you're really into the American system, it can be 32 feet per second squared, which is interesting because when I took calculus and we were doing these problems in calculus, they didn't use the metric system, 9.8 meters per second squared. They used the 32 feet per second squared, which is really weird. But in calculus, we're doing these equations by doing the derivative. We're not even using these formulas, right? So, so you already know these, right? You already know these equations here. You already know those equations there, that one up there. The new ones, this is literally the same thing. These two are the same thing, right? Gravity and acceleration right here. And then the last one is this one here for centripetal, right? So I don't anticipate asking you any more questions about the ones you've already learned. So really the only one you need to remember, these easy ones like, um, yeah, the easy ones for the centripetal acceleration and the one for um, gravity. Those are the only two you need to know. Nice little plug and play going on there, right? I mean, plug and chug. And that actually ends today's lecture.